Okay, in this video we are going to talk a little bit about KW. We're going to review some titration techniques from Chem 20, and we're going to look at a little bit different of a titration calculation that sometimes shows up in Chem 30. Okay, so first thing we're going to talk about is KW. So we've already talked about KC, right? And that was our equilibrium constant. When we use KW, this is specifically for water, hence the W. So when we look at water, water actually has the ability to do something that a lot of other chemicals can't do. And it has the ability to self-ionize. So what that means is one water molecule can react with another and produce hydroxide and hydronium, right? We talked a little bit about this when we were talking about amphiprotic species in the last video. So what we find is that at 25 degrees Celsius, which is room temperature in chemistry, the concentration of hydroxide is equal to the concentration of hydronium, which makes sense because if you look at this, we would create an ice table for this, right? It's an equilibrium equation. We would have the hydroxide and the hydronium both starting at 0. Their change values would be plus X, and their equilibrium concentrations would simply be X. So they're both X, which is why they are both 1.0 times 10 to the negative 7. So if we were to write out the KW expression for this, we would simply have hydroxide times hydronium, right? We would leave the water out because water is a liquid, and we said that liquids and solids don't belong in our K expressions. So if we take those two concentrations, so 1 times 10 to the negative 7, and multiply it or square it, we wind up with 1.0 times 10 to the negative 14. So this is known as our water constant. Okay, this can be found in your data booklet. I at home have this lovely yellow data booklet, a little different from the red one you have. Mine dates from 1995. So it's going to look a little different on the inside. I don't know if this has a miscellaneous chart. Oh, it does. Look at that. Still the same, however many years later that is. So here on page 3, you're going to find that you have a chart. It's called the miscellaneous chart. And inside of there, you are going to find that it gives you KW as 1.0 times 10 to the negative 14. So you don't have to memorize it. So where I would use KW. I would use KW if I knew the hydroxide and I was trying to find the hydronium, or I knew the hydronium and I was trying to find the hydroxide. Okay, it's a faster way than what you would have done in Chem 20. In Chem 20 with a question like that, you would have taken the hydroxide, you would have turned it into a POH, which you then would have converted into a pH, which you then would have used to calculate the concentration of hydronium. But now we can plug in this 1.0 times 10 to the negative 14 for KW, plug in whichever of these two numbers we know, and then we can solve for the other one, okay? So pretty common actually to see a question on the diploma that's literally just converting between hydroxide and hydronium. So it is really helpful to make sure that you are familiar with the KW equation. Okay, electrolytes and non-electrolytes. Not really sure why I have this slide here, to be honest. You already know what electrolytes and non-electrolytes are. In a way, though, we generally talked about how molecular compounds are non-electrolytes in solution. Some of you, though, when you did your lab last year in Chem 20, actually found that everything conducted. And part of the reason you find that is water is technically an electrolyte, right? It does produce hydronium and hydroxide. Produces them at super low concentrations. So if you don't have a good conductivity meter, it's never going to pick it up. But if you have a really strong conductivity meter, which we actually have some pretty decent ones in the school, you will sometimes find that molecular solutions will conduct. And that is because the water self-ionizes and you do have some ions present in solution. Okay, titrations. Okay, we are going to spend more time in this unit looking at titrations. Today we're just going to kind of briefly talk about it and review some terms and some key pieces. So when we do a titration, you are going to set up your titration apparatus, right? And some of you did this in first semester, but those of you who took it second semester of last year never actually did a titration. So a titration is a skill. A few people are just like naturally gifted and are going to be really good at doing a titration their very first time. Most people, including myself, are not gifted in that way and struggle significantly with getting to that endpoint of their titration, getting the right color. Right? So if you remember last year, you have your Erlenmeyer flask that sits on the bottom, you have your retort stand with its little burette clamp, and then you put your burette inside of there. We fill the burette with one chemical, and we fill the Erlenmeyer flask with the other. Because we were doing acid-base titrations, we added an indicator to the Erlenmeyer flask so that it would indicate to us when we had reached the end point, right? So last year we talked about two terms. We talked about an end point and we talked about an equivalence point. Important to recognize the difference. So an end point is when your indicator changes colors and tells you to end your titration. An equivalence point is when the moles of acid and base are present in equal concentrations, obviously assuming that our balanced equation is a 1-to-1 ratio. If it wasn't a 1-to-1 ratio, they wouldn't be equal. They would be present in proportions that relate to the 2-to-1 or 3-to-1 that we have in that balanced equation, okay? So in an ideal world, our endpoint and our equivalence point are going to line up, right? That's why we choose our indicators carefully when we do acid-base titrations. And generally, we choose an indicator that's going to change colors around 7 because that's going to ensure that our endpoint and equivalence point are going to be the same. Obviously, if we overshoot our endpoint, which sometimes happens, or many times happens, then we don't have our endpoint and equivalence point lined up because we have actually gone too far, right? So if you remember last year, we did 2 sets of titrations. One used bromothymol blue and one used phenolphthalein. You guys tend to be better with the bromothymol blue because it goes from yellow to green to blue, and it's pretty easy to see I have green versus I have blue. Although sometimes, as some of you saw last year, when you stare at the yellow long enough, you start to see colors that aren't there. The phenolphthalein tends to be the trickier one because you go from colorless to pink, and our end point is the faintest hint of pink. But a lot of times you guys go until you see like a dark pink, at which point you have actually overshot the end point and have gone too far, okay? So, potentially, you guys are going to be doing a review titration. Hopefully, I will be able to find a sub to come in who can do that lab with you guys because it is definitely an important skill to have before we do our Chem 30 titration. But we will kind of play that by ear and figure that out as we go. So when we do our titration, important to remember that titration number 1, I'm usually going to just kind of open it and let it run for a bit. And I'm going to close it usually after 5 mils, and then I'm going to open it again for 5. And we're going to keep doing that until my indicator changes colors. Generally, I'm not going to record the first one I do. And that's because the point of the first one is just to give me an idea of where the volume is going to change. Because for my first one, I have no clue if it's going to be 7 mils, 12 mils, 20 mils. I don't know what the number is going to be. So kind of just opening it, but I don't waste a lot of time on a titration that probably is going to get thrown away anyways. So titration number 1 is more of an experiment to figure out where the volume is. And then titration number 2 is going to be your first real try, where now you have an idea of, oh, it changed somewhere between 12 and 13. So maybe I'm going to add the first 11 mils all in one fell swoop. I'm going to make sure that I stir it, make sure that the color goes back to the original color, and then I'm going to start going really slowly and carefully and adding drop by drop. And then when I see that it's starting to last longer for the color to go away, that's when I'm going to start doing the half drops and the quarter drops, right? And that's where you open the little valve just a little bit and you get a little bit of a bubble hanging off, and then you touch the side of the inside side of the Erlenmeyer flask to it, and then you kind of swirl it around a bit to try to mix it down into your solution, okay? So titration calculations, there's kind of 2 ways that you will see titration calculations if you remember back to Chem 20. One way was they gave you experimental data. Usually they're going to give you 4 trials. A general rule of thumb is that 1 trial, if you're given multiples, should almost always be eliminated. There are some exceptions where you won't be able to eliminate, but generally you're looking for the one that isn't like the others. So if it gives you colors and 3 are light pink and 1 is dark pink, you're going to get rid of the dark pink. If it doesn't give you colors, but instead gives you volumes, you're going to find the volume that is the furthest away from the others, and you are going to eliminate that one. Once you do that, you're going to average the total volumes and then just do the one stoich calculation. Okay, the other Chem 20 style was it didn't give you a data table and it just said like the initial and the final volume of the burette, and then it gave you a concentration and a volume of acid. And then you were just, again, able to do that stoich calculation. So here's kind of that type of example, right? So 25 mils of sodium hydroxide is titrated with a 0.100 mole per liter solution of hydrochloric acid. If the initial burette reading is 0.50 mils and the final is 35.25, what is the concentration of the sodium hydroxide? So Chem 20 stoich, right? We're going to combine the hydrochloric acid with the sodium hydroxide. Okay, titrations, even though we are in equilibrium, titrations are always going to be single-headed arrows. Okay, the reason they're always going to be single-headed arrows is we're always continually adding the reactant, right? You think about our titration, we're always opening the valve and we're adding more. So because of that, hold on, I'm gonna pause. Sorry about that. Someone was getting ice cubes out of the fridge. It was very loud. Okay, so HCl plus NaOH, like I said, these are always going to be single-headed arrows in a titration because we're continually adding a reactant, so we're forcing it to go to completion. So product-wise, we are going to make water and sodium chloride, or salt, which is going to be aqueous. So givens-wise, we were given a volume of sodium hydroxide, so we have 0.025 liters. The concentration of HCl was given to us, or I'm having issues, as 0.100 moles per liter. Now I'm having more issues of overlapping. Okay, and then what were we told? So the initial burette reading is 0.5 and the final is off the screen, which is helpful. 35.25. So we're going to do 35.25 minus 0.5. So this 0.50 is not going to count for significant digits because I'm not actually using it in my calculation. What I do need to recognize though is that I'm doing a subtraction with this, 2 numbers after the decimal, 2 numbers after the decimal. So whatever number I get out of that subtraction can go up to 2 numbers after the decimal. So I get 34.75, so it's going to be 0.03475 liters. Okay, so both the 7 and the 5 get to stay because it was 2 numbers after the decimal. And I know I moved my decimal at the same time as I wrote that, but that is going to have 4 significant digits. So even though this here has 2, my final answer actually can go to 3. And the reason for that is this has 3. Sorry, I added that 0 because I dropped it. And then this has 3. And this has 4, okay? So we can go to 3 significant digits. So we are looking to find the concentration of sodium hydroxide. And now I'm gonna pause again because now my dog wants to go outside. Okay, so we are looking for the concentration of sodium hydroxide. So unit-wise, we're looking to get moles of NaOH per liter. So I can start with my mole ratio. So 1 mole of NaOH over 1 mole of HCl. Okay, we need to get rid of moles of HCl, so I can use the concentration. So we're going to do times 0.100 moles of HCl per liter. Okay, so this is where sometimes you guys get a little confused. So moles of HCl cancels. And now sometimes you guys look at units and you're like, oh, we have moles per liter, I'm done. But really important to recognize that this liters is for the HCl, and we're trying to find the concentration of sodium hydroxide. So we need to make sure that the liters that we have down there are actually the liters of NaOH. So where we're gonna go from here, we need to get rid of the liters of HCl. Perfect, we have liters for HCl. So we are going to times by 0.03475 liters, and we can just put that over 1. Okay, that now allows for us to eliminate the liters of HCl. We now just have to introduce liters of sodium hydroxide. We know it has to go on the bottom, so we're going to do 1 over 0.0250 liters. Okay, so now we have moles of sodium hydroxide per liter, so we can go ahead and calculate that concentration. Okay, you should be coming up with 0.139 moles per liter, or you can just use that capital M like we've talked about so far this year. Okay, so Chem 20 style calculation, write your balanced chemical equation, list your givens, do your unit analysis, make sure you're being careful with those liters and that you do have the right liters at the end. Okay, so this was the other type of one we saw last year, right? So this is where you're going to see that there are multiple trials. So you can see that in this particular example, they stopped after 3 trials. They didn't bother doing a 4th. And the reason they didn't bother to do a 4th is they didn't have to. They already had 3 sets of results that were all within 0.2 mils of each other. So either number 4 would have agreed with those numbers, or we would have dismissed the number as our outlier from our data, okay? So in this case, you can average them. It's just going to give you the 12.6 mils. You now know the volume you're doing, write your balanced chemical equation, and go ahead and do your unit analysis. So what I do want to do is one additional example, which sorry is not in your notes. So if you want to pull out your practice problem book, maybe pause the video for a minute while you guys all get that out. So in that booklet, you want to go to the worksheet that's called Acid Bases, Titrations, and Mixtures. I'm going to show you how to do number 1 off of this worksheet. And you're going to find that all the remaining questions are all going to be super similar in what you are going to do. So these are titration questions, but they're a little bit different, because instead of asking you to determine the volume or the concentration of one of them, it's going to give that all to you. So it says determine the concentration of the hydronium ion of the solution resulting from the mixture of 20 mils of 0.2 mole per liter HCl and 50 mils of 0.03 molar sodium hydroxide. So this doesn't look like this, but this is technically a limiting reagent question, right? And if you remember back to last year with some of those limiting reagent questions, we kind of talked about how much remains. That is what these questions are getting at, and they do sometimes pop up. So start this by doing the same thing as always. We're going to write our balanced chemical equation. So we have HClAq plus the NaOH, and that is going to give us H2O. Shift that over. There we go. H2O liquid plus NaCl. Okay, so givens wise, I might just space those out a little more. I don't know what I just did. Hold on. I pressed some button that did something weird. Oh, not what I wanted either. Slowly getting there. All right, okay. Now that I fixed that, so we're going to list our givens. So for HCl, we know that we have 0.02000 liters. We know that it's a concentration of 0.200 moles per liter. Okay, then for sodium hydroxide, we know that we have 50 mils, so 0.05000 liters. And we know that our concentration is 0.300 moles per liter. Okay, so this already looks a little bit different than the last one we did, because the last one we did, we didn't have this. We were looking for that. So when you see that it gives you both, what we need to do is we need to figure out what the limiting reagent is. So simplest way to do that in a question like this, because it's a 1-to-1 ratio between our reactants, which you're going to find for most questions like this, it is a 1-to-1 ratio. We can just calculate how many moles we have based off of the concentration and the volume. So if we look at the HCl, right, we can take this data and we can calculate how many moles we have of it, right? So if I want to figure out how many moles of HCl I have, because I have moles per liter in liters, all I have to do is times them. So we can do that 0.200 moles, put that over a liter, and then we can times it by 0.02000 liters. Okay, that is going to allow for us to determine how many moles we have of HCl. Okay, so do that in your calculator, 0.2 times 0.02. So for HCl, we have 0.00400 moles. Okay, now we're going to do the same thing for the sodium hydroxide. So we're going to take the data for the sodium hydroxide, and we are going to determine how many moles we have. So we're going to figure out N of NaOH. So same deal, we're going to take the concentration and we're going to multiply by the volume. So we're going to do 0.0300 moles over liters. And then we are going to times by that 0.0500 liters. Okay, so from here we're going to figure out how many moles of sodium hydroxide we have. So 0.03 times 0.05. We have 0.0015 moles. So because it's a 1-to-1 ratio between the two of them, we have more moles of HCl than we do of sodium hydroxide. And if you remember back to limiting reagents, we always said whichever one you have the least of is the one that you are going to entirely consume. So that is telling me that the NaOH is my limiting and the HCl is my excess. So where this question now goes to, right, if you think about what it was asking us, it's to determine the hydronium ion concentration of the resulting solution. So if I have 0.0015 moles of sodium hydroxide, and that's my limiting reagent, and it's a 1-to-1 ratio between the two of them, I am going to use up the same amount of HCl. So what I can now determine is how much HCl is going to be left, right? So once we do that neutralization, how many moles of HCl are going to remain? Okay, we're going to determine that by just getting the difference between these. So we're going to take the 0.00400 moles, and we are going to subtract the 0.0015 mole. Okay, and note, I wrote it as 0.0015, but it does technically have an extra zero in there for significant digits. And that zero didn't add in the way I meant for that zero to add in. Let's see if I can shift that. There we go. We'll just squeeze that right in there. All right, so now we're going to do our 0.004 minus 0.0015. So that is going to tell us that the moles of HCl that remain are going to equal 0.0025 moles. So now we've neutralized all the sodium hydroxide. There is none left, but we have hydrochloric acid in excess. The question is asking us to determine the concentration of hydronium. We've now determined how many moles of HCl we have. So now what we need to do is write an ionization equation, because we have that hydrochloric acid. It's now basically hanging out in water or salt water, right? So we have that turning into hydronium and a chloride ion. Which is good because this is what we're trying to find, right? The question has asked us to find the concentration of the hydronium. So what do I know? Well, I know how much HCl I have, right? I know that there's 0.0025 moles. But to get concentration, I also need to know what the volume is. So going back to the question, we have to consider the fact that we had, let's say, an Erlenmeyer flask, and we put in 20 mils of HCl. We then added 50 mils of sodium hydroxide. So if I put 20 mils and I put 50 mils all into this container, the current volume of my solution is 70 because I combined them together. So right now, as I'm trying to figure out the concentration of hydronium, I have to use the total volume of the solution, not just of the HCl, because they're all combined together inside of that container. So the volume for this is going to be 0.0700 liters. Now I have the information that I need to be able to calculate the concentration of the hydronium. So we can start with our ratio. So 1 mole of H3O plus, and that is going to be over 1 mole of HCl. Okay, then we know how many moles we have of HCl. So we can times by 0.0025 moles of HCl. And we're going to put that over 1, right? Because there is no bottom part to that. So that now allows for us to get rid of moles of HCl. We need to introduce the liters. That's where we're going to use that 70. So we're going to do times 1 over 0.07000 liters. Okay, so now I have moles of H3O plus per liter. So 0.0025 divided by 0.07. I'm going to come up with 0.0357. How many significant digits can I have? Let's go all the way back up. So 3, 3, 3 goes off, but also 3. Okay, so 3 significant digits, so 0.0357. That'll be moles per liter, or you can use the capital M. Okay, if you look at some of the other examples on the sheet, they talk about getting a pH. So if you think about it, now that I have hydronium, if a further example asks me to calculate pH, I would just do negative log of whatever my answer is. Okay, I rounded this for significant digits because this was the last thing the question asked me for. But if it was asking me for pH, I would want to use the whole button in my calculator, the answer button, I should say, on my calculator, to go about calculating what that pH is. Okay, so booklet-wise, you can now work on the KW questions, and you can also work on that titrations and mixtures worksheet. Okay, ideally tomorrow you guys are going to be doing an acid-base titration, a Chem 20 style one. Again, it's just going to depend on who I find to come in while I'm out for the next little while. Okay, again, if you have questions, you have issues, please feel free to email me. I'm sitting at home with my computer in front of me, drinking tea, listening to my children run around, sick but not sick. Okay, all right, thanks.